Have you ever tried this? Go ahead, touch something made of metal. Now touch a piece of wood sitting right next to it. The metal feels cold. The wood feels warmer, right? That's not surprising. In fact, it feels so obvious that you probably never questioned it. Metal is cold. Wood is warm. Everyone knows that. It's something you've experienced your entire life. Door handles, railings, tools, metal always has that cold bite to it. But here's the strange part. If both of those objects have been sitting in the same room for a while, they're actually the exact same temperature. Not close, not similar, the same. So now you've got a problem. Because your hand is telling you one thing, and reality is telling you something completely different. And here's the twist. Your hand isn't broken. It's not lying either. It's just not doing what you think it's doing. Your hand is not a thermometer. And once you understand what it's actually measuring, you'll never trust your sense of touch the same way again. Now, to be fair, this belief doesn't come from nowhere. It feels true for a reason. Think about it, your entire life has been one long experiment. Every time you've touched metal, a coin, a railing, a door handle, it had that same sharp, cold feeling. And every time you've touched wood, a mother chair, a desk, it felt softer, warmer, more neutral. Over and over again, the result never changes. So your brain does what it's designed to do. It finds patterns. Metal equals cold. Wood equals warm. Simple, reliable, proven by experience. And this isn't just some childish assumption. Even highly educated people pause when you challenge this idea, not because they don't understand science, but because the sensation feels like direct evidence. You're not guessing. You're not imagining. You're literally touching the object and feeling the difference with your own skin. It feels as real as it gets. And that's exactly why it's so convincing. Because the illusion isn't random, it's consistent. Every single time, your senses give you the same answer. And when something is that repeatable, your brain stops questioning it. It upgrades it from a feeling to a fact. But that's where the mistake begins. So let's test this belief in the simplest way possible. Take a real thermometer and place it on a metal object. Now, take the same thermometer and place it on a piece of wood right next to it. Wait a few seconds. What do you expect it to show? 2 different temperatures? It doesn't. It gives you the exact same reading. Because if both objects have been sitting in the same room long enough, they've reached the same temperature as the air around them. The metal isn't colder. The wood isn't warmer. They are, physically, identical in temperature. And now you're stuck with a contradiction. Your hand is telling you one thing. The thermometer is telling you another. So which one do you trust? Because your hand isn't malfunctioning. The sensation is real. You genuinely feel a difference the moment you touch them. But the thermometer isn't wrong either. Which means the problem isn't in the sensation. It's in how you're interpreting it. You're feeling something real, just not what you think you're feeling. So what is your hand actually measuring? Most people assume something very simple. You touch an object, and your skin reads its temperature, like a built-in thermometer. But that's not what's happening. Not even close. Your skin never directly measures the temperature of the object you're touching. It can't, because your nerve endings don't reach into the metal, or the wood, or anything outside your body. They're embedded in your skin, and all they can do is monitor what's happening right there locally. What they're really detecting is the temperature of your own skin, and more importantly, how fast that temperature is changing. Are you heating up, or are you cooling down? And how quickly is that happening? That's the signal your brain receives. So when you touch something and it feels cold, what's actually happening is your skin temperature is dropping. And if it drops quickly, your brain interprets that as very cold. If it drops slowly, the sensation feels mild or even neutral. Same with heat. A rapid increase in skin temperature feels hot. A slow increase feels gentle or warm. So your hand isn't measuring temperature out there in the world. It's measuring temperature changes right here in your skin. And once you understand that, the real question completely changes. It's no longer, why is metal colder than wood? Now the question becomes, why does metal pull heat out of your skin so much faster than wood does? To understand what's really going on, we need to clear up one crucial idea. Heat and temperature are not the same thing. Most people use those words interchangeably, but in physics, they mean completely different things. Temperature is simple. It's a number that tells you how energetic the molecules in something are. The faster they're moving and vibrating, the higher the temperature. The slower they move, the lower the temperature. So, temperature is a state. It describes how something is right now. But heat is something else entirely. Heat is energy in motion. It's what happens when there's a temperature difference between two things, and energy starts flowing from one to the other. Hot to cold. Always. So heat isn't something an object has sitting inside it. It's a process. A transfer. Energy moving from one place to another. And that distinction changes everything. Because when you touch something, you're not feeling its temperature directly. What you're actually experiencing is heat flow. Energy moving either out of your skin or into it. Fast flow feels intense. Slow flow feels mild. So the sensation of hot or cold isn't about how hot or cold something is. It's about how quickly energy is moving between you and it. So now we can finally answer the real question. Why does metal feel colder than wood? Start with something simple. Your body is warm. Your skin sits at around body temperature, while the objects around you, metal, wood, plastic, are usually cooler than that. So the moment you touch anything, heat begins to flow from your finger into the object. That part is always true. But here's where things start to diverge. Not all materials accept that heat at the same rate. Metal is incredibly good at pulling heat away from your skin. The moment you touch it, energy starts rushing out of your finger, fast. Your skin temperature drops quickly, and your brain interprets that rapid drop as a strong cold sensation. Wood behaves very differently. It still pulls heat from your skin, but much more slowly. So your skin cools down gently, barely enough to trigger that intense cold signal. Same starting temperature, same finger, completely different experience. And the difference comes down to one thing: speed. Here's a way to picture it. Imagine your finger is like a container full of water, and that water represents heat. Now imagine you're pouring that water into a funnel. If the funnel is wide and drains quickly, the water disappears fast. That's metal, a fast drain. But if the funnel is narrow and slow, the water backs up and drains gently. That's wood, a slow drain. The amount of water is the same, but the speed at which it leaves changes everything. And your brain is extremely sensitive to that speed. Fast loss feels cold. Slow loss feels normal. So metal doesn't feel cold because it is colder. It feels cold because it's better at draining heat from your body. Now let's zoom in even further, down to the atomic level. This is where the real difference between metal and wood begins to show. Metals have something special inside them. They contain what physicists call free electrons. These are electrons that aren't tightly locked to a single atom. Instead, they move freely throughout the entire material, almost like a fast-moving cloud flowing through a lattice of atoms. And this changes everything, because the moment you touch metal and heat starts entering its surface, those free electrons instantly pick up that energy and carry it away through the material. Fast, efficient, almost instantly. So the heat doesn't stay near your fingertip. It doesn't linger on the surface. It gets rapidly distributed throughout the metal. That's why the surface keeps feeling cold. It never gets a chance to warm up. Now compare that with wood. Wood has no free electrons. Its atoms are locked into rigid molecular structures, and energy can only move by a much slower process, one atom vibrating, passing energy to the next, and then to the next. It's like trying to move information through a long chain by tapping shoulders. Slow, inefficient, delayed. So when your finger touches wood, the heat has nowhere fast to go. It stays near the surface, warms it up quickly, and reduces the temperature difference between your skin and the object. And when that difference shrinks, the cold sensation fades. This is also why metals are such good conductors of electricity, because the same free electrons that carry heat also carry electrical charge. One system, one mechanism, two different effects, and that's the beauty of it. What feels like a simple cold sensation on your skin is actually the result of electron-level physics happening at incredible speed right beneath your fingertip. Now, to make all of this fully complete, we need two key properties, because not all materials behave the same way when it comes to heat. The first is thermal conductivity. This is a measure of how quickly heat can move through a material once it enters it. In simple terms, it answers a basic question. If heat gets inside this material, how fast can it spread out? Metals score extremely high on this. Heat doesn't stay in one place, it moves quickly, spreads efficiently, and disappears deep into the material almost instantly. Wood, on the other hand, has very low thermal conductivity. Heat moves through it slowly, almost reluctantly. It tends to stay near the surface, instead of spreading through the bulk. But here's the important part. Thermal conductivity alone doesn't fully explain what your hand feels. For that, we need a more important concept: thermal effusivity. This is the property that actually determines how something feels to touch. Thermal effusivity describes how quickly a material can absorb heat from your skin at the moment of contact. Not just how heat moves inside the material, but how aggressively it pulls energy out of your body right away. A material with high effusivity acts like a heat sink. The moment you touch it, it rapidly draws energy from your skin, causing your skin temperature to drop quickly. And that rapid drop is what your brain interprets as cold. Metals have very high effusivity. That's why they feel so cold, so instantly. Wood has low effusivity. It absorbs heat slowly, gently, without triggering that sharp sensation. So even at the same temperature, different materials don't just behave differently physically, they feel completely different. And the key to that difference isn't just conductivity, it's effusivity, the property that controls how your body experiences heat transfer in real time. Now let's make this real, because once you understand the physics, you start seeing it everywhere, in daily life. Let's break it down into simple examples. A. Flooring. Think about walking barefoot into a bathroom early in the morning. If the floor is made of tile, it feels cold, almost unpleasantly cold. But if you step onto a carpet or rug right next to it, it feels much warmer. Here's the twist. Both surfaces are usually at the same room temperature. The difference isn't temperature. It's how fast they pull heat from your feet. Tile transfers heat quickly, so your skin temperature drops fast, and your brain reads that as cold. Carpet traps air, slows heat transfer, and barely pulls heat from your skin, so it feels warm. B. Utensils. Now think about a spoon sitting in a pot of hot soup. A metal spoon becomes so hot that you can barely touch the handle, but a wooden spoon stays comfortable to hold, even though both are in the same boiling liquid. The difference again is heat transfer speed. Metal rapidly conducts heat from the soup all the way up to your hand. Wood is slow. It barely carries that heat upward, so the handle stays relatively cool. Same soup, same temperature, completely different experience. C. Insulation. Now think about something like oven mitts. You can pull a tray out of a 200 degrees Celsius oven with your bare hands. If you didn't have protection, you'd get burned instantly. But with thick mitts, you're fine for a few seconds. Why? Because the mitts don't stop heat from existing. They just slow it down dramatically. They trap air inside their fibers, and that trapped air is a very poor conductor of heat. So heat takes time to travel through the material, and in those few seconds, your skin doesn't heat up enough to cause damage. D. Extreme example. Styrofoam. Now take something even more extreme, styrofoam. Even if you take it straight out of a freezer, it doesn't feel brutally cold in your hand. It feels almost neutral. Why? Because styrofoam is mostly trapped air, and air is one of the worst conductors of heat in nature, so it simply cannot pull energy out of your skin fast enough to create a strong cold sensation. Even though it is cold, your body barely feels it. And all of these examples point to the same idea. What you feel as hot or cold is not about the actual temperature of an object. It's about how fast heat moves between it and your body. There's another piece of this puzzle that often gets overlooked, because so far, we've only talked about the object you're touching, but the other half of the system is you. Your body is not passive in this process. It's constantly active. Your body is generating heat all the time through metabolism. Every second, your cells are producing energy, and a lot of that energy becomes heat. At the same time, your circulatory system is doing something very important. It's constantly sending warm blood out to your skin to keep it at a stable temperature. So your skin isn't just sitting there waiting for the environment to affect it. It's being actively regulated. Now here's where things become interesting. The sensation of hot or cold doesn't depend only on how much heat you're losing. It depends on the balance between two forces: how fast you are losing heat to the environment, and how fast your body can replace that lost heat. If heat leaves your skin slowly, your body keeps up easily. Your temperature stays stable, and you feel comfortable or neutral. But if heat leaves your skin rapidly, your body can't replace it fast enough. Your skin temperature drops, and your nervous system interprets that drop as cold. So the feeling of cold is not just about the environment being cold. It's about your body losing heat faster than it can produce and restore it. That's the real threshold your senses are responding to. Not temperature itself, but thermal balance. Now let's push this idea into extreme conditions. Because this isn't just a curiosity about door handles or spoons. It can become dangerous in the real world. Take metal in freezing weather. On a cold winter day, a metal railing or pole might be at or below freezing temperature. The air around it might feel cold, but still manageable. But the moment you grab that metal with bare skin, something very different happens. Heat doesn't just leave your hand slowly. It gets pulled out rapidly. Your skin temperature drops fast enough that your body can't compensate in time. And that's where things become serious. Because rapid heat loss isn't just uncomfortable, it can start to damage tissue. Now compare that with air at the same temperature. Air feels cold? Yes, but it's a very poor conductor of heat. It doesn't pull energy from your body quickly. That's why you can breathe freezing air or walk through it for a while and still survive comfortably with proper clothing. Same temperature, completely different effect. Now here's an extreme example that makes the physics impossible to ignore. Touching your tongue to a metal pole in freezing conditions. It sounds like a dare, but the science behind it is very real. The moisture on your tongue freezes almost instantly because the metal draws heat away so fast that ice crystals form in seconds. And once that happens, your tongue can actually stick to the metal surface. Not because the metal is colder than air in some magical way, but because it is an extremely efficient pathway for heat to escape your body, fast enough to cause immediate freezing at the point of contact. And that's the key idea again. It's not just temperature that matters. It's the rate at which heat leaves your body. Now here's something that really reveals what's going on. Let's reverse the situation. Instead of touching metal and wood at room temperature, heat both of them above your body temperature. Say around 50 degrees Celsius. Now try touching them. What happens? The metal suddenly feels extremely hot, almost painfully so, but the wood feels warm, even comfortable in comparison. Same room, same experiment setup, same idea, but completely different sensation. And here's the key insight. Nothing about your senses has changed. What's changed is the direction of heat flow. Before, heat was moving from your hand into the object. That's why metal felt cold. It was pulling energy away from you very quickly. Now, heat is moving from the object into your hand. And metal doesn't just transfer heat quickly in one direction, it does it in both directions. So now, it's flooding your skin with energy at a much faster rate than wood does. Your skin temperature rises rapidly, and your nervous system interprets that rapid increase as intense heat. Meanwhile, wood transfers heat slowly, so the warming effect is gentler and less intense. So again, the sensation depends on two things: the direction of heat flow and how fast that heat is transferred. Reverse the direction, and you reverse the feeling. But the underlying physics never changes. Now let's take a step further and understand something that explains almost all temperature protection in everyday life. Insulation. At its core, insulation is surprisingly simple. It doesn't remove heat. It doesn't cancel heat. It doesn't stop heat from existing. It only does one thing. It slows down the rate at which heat moves. That's it. Now imagine you place a barrier between your skin and a hot or cold object. It could be cloth, air, foam, or any similar material. What that barrier does is interrupt the flow of energy. Heat still wants to move from hot to cold, always, but now it has to pass through a material that is very bad at transferring it. So instead of flowing quickly, it moves slowly. Very slowly. And if it moves slowly enough, your body doesn't have time to respond strongly. Your skin temperature barely changes in that short window. And that's what keeps you safe or comfortable. Now here's the most important rule in all of insulation. The weakest conductor in the chain controls everything. It doesn't matter how conductive one layer is if another layer is extremely resistant to heat flow. Because heat can only move as fast as its slowest pathway allows. That's why a thin layer of cloth can dramatically reduce the cold feeling of metal. That's why oven mitts work even in extremely hot environments. And that's why even something as simple as trapped air can outperform solid materials in insulation. In every case, the system is governed not by the strongest conductor, but by the weakest one. Now let's look at 3 everyday environments that make this effect even more obvious: air, wind, and water. Because each one changes how heat moves from your body in a very different way. Air. Let's start with still air. Air is actually a very poor conductor of heat. That means it doesn't transfer energy very efficiently. So when the air around your skin is still, something interesting happens. Your body warms up a thin layer of air right next to your skin, and that thin layer acts like a natural insulating blanket. It slows down further heat loss and helps your body maintain a stable temperature. That's why still air can feel much more comfortable than you'd expect, even in cooler conditions. Wind. Now introduce wind. Wind completely changes the situation, because instead of letting that warm layer of air sit near your skin, it constantly strips it away. Fresh cold air keeps replacing it again and again, so your body never gets the chance to build that insulating layer. Heat keeps escaping continuously, and the rate of heat loss increases sharply. That's why wind feels so much colder than still air, even when the temperature is exactly the same. It's not a change in temperature. It's a change in heat transfer. Water. Now let's move to water. Water is a completely different case. It conducts heat far better than air, and it also has a very high heat capacity. That means it can absorb a huge amount of energy without changing temperature very much. So when your body enters cold water, heat doesn't just leave your skin quickly. It gets absorbed and carried away efficiently, while the surrounding water stays cold. There's no insulating layer forming, no buffering effect like air, just continuous, efficient heat loss. That's why water feels so much colder than air at the same temperature, and why hypothermia develops so much faster in water, because your body is losing heat far faster than it can replace it. And once again, the pattern is the same. Different environments don't just change how cold something is. They change how fast heat leaves your body. Now, step back for a moment and ask a deeper question. Why does our body work this way at all? Why don't we directly sense temperature itself? The answer becomes clearer when you think in terms of survival, not physics. Because your body doesn't actually need to know the exact temperature of everything you touch. Knowing that a surface is 22 degrees Celsius or 5 degrees Celsius doesn't help you survive. What does matter is something far more important. Are you losing heat dangerously fast or not? Because your survival depends on maintaining a stable internal temperature. Too much heat loss, and your body cools down to dangerous levels. Too much heat gain, and you risk overheating. So over time, evolution didn't optimize your senses to measure temperature precisely. It optimized them to detect risk. And risk, in this case, comes from how fast energy is moving in or out of your body. That's why your nervous system is tuned not to absolute temperature, but to the rate of temperature change in your skin. A rapid drop signals danger. A rapid rise signals danger. Slow changes are ignored or felt as neutral. So what you experience as hot or cold is really your body asking one question: how fast am I losing or gaining heat right now? And that's the question your senses were built to answer, not with scientific precision, but with survival urgency. Now we can finally step back and see what's really going on. Because everything we've discussed leads to one clear realization. Your hand is not a thermometer. It was never designed to measure the temperature of the world around you. Instead, it is something far more interesting. It is a heat flow sensor. It doesn't report how hot or cold an object is. It reports how fast energy is moving between that object and your body. That's the raw signal your nervous system receives. Heat leaving your skin, or heat entering it, fast or slow. And everything you feel, warm, cold, neutral, painful, is your brain interpreting that flow of energy. So, sensation is not direct reality. It is an interpretation, a translation of physics into experience. And once you understand that, the illusion disappears. Metal doesn't feel cold because it is cold. It feels cold because it removes heat from your body quickly. Wood doesn't feel warm because it is warm. It feels warm because it barely removes heat at all. Your hand is doing exactly what it was built to do. It's just not doing what you thought it was doing. If you zoom out even further, something interesting starts to emerge. None of your senses actually show you reality directly. They don't give you the world as it is. They give you interpretations of physical signals. Take vision. You don't see objects themselves, you see light bouncing off them. Your eyes are interpreting wavelengths of electromagnetic radiation, and your brain turns that into color, shape, and depth. Take hearing. You're not directly sensing sound out there. You're detecting pressure waves in the air, vibrations that your brain translates into pitch, rhythm, and meaning. And touch is no different. What feels like temperature is actually your nervous system interpreting heat flow energy moving into or out of your skin. So across all your senses, the pattern is the same. You are not experiencing raw reality. You are experiencing a biological translation of physical signals. And that's where physics comes in. Because physics is what describes what is actually happening underneath all of that interpretation. It doesn't care about how things feel. It describes energy, motion, transfer, and structure as they truly are. So when you combine both perspectives, something powerful becomes clear. Your senses are not wrong, but they are not complete either. They are built for survival, not precision. And physics is the tool that reveals what's happening beyond the limits of perception. So let's come all the way back to where we started. Metal feels cold. Wood feels warm. That was the mystery. But now we know the truth. Metal isn't cold. It's just far better at stealing heat from your body. That's the real difference. Not temperature, not sensation, but the rate at which energy moves between you and the material. And once you see it this way, the illusion disappears completely. What you call cold is just fast heat loss. What you call warm is just slow heat loss. Nothing more than physics playing out at your fingertips. But here's where it gets interesting. Because this raises a much bigger question. If your sense of touch can mislead you like this, what else are your senses getting wrong? How much of what you feel, or see, or hear is actually reality? And how much is just interpretation? And that's the real takeaway here. Simple questions like why metal feels cold don't stay simple for long. They open the door to deeper and deeper layers of physics, until you realize that even the most ordinary experiences are built on extraordinary science happening just beneath your awareness.